So why would giving your students or kids a whole lot of problems to solve in the lesson be not the best way to actually get them to learn? Well, Sweller is going to try and answer this for us in this paper written a long time ago. um, so it's in 1988. It's in cognitive science. And the title of the article, this brilliant article, is Cognitive Load During Problem Solving, Effects on Learning. So what happens to your cognitive load when you're problem solving? What kind of effect does it have on learning? Does it improve learning or does it actually take away from learning? So let's look at the abstract because it's really clearly laid out. And he starts off by saying that there's considerable evidence indicating that domain-specific knowledge, right? So domain-specific knowledge is a special knowledge of a special area that's built up in a systematic way. So it's kind of like you know what's going on in a specific area. And we call that schemas, right? It's organized knowledge in your brain. And that's the primary factor that distinguishes experts from novices in problem-solving skill. So, evidence that conventional problem-solving activity is not effective in schema acquisition. Now, just hold on to that. Because firstly, what he's saying here is that there's evidence, right? So we've got to check out the evidence. And the evidence is that your conventional problem-solving activity, that kind of time you have in the class where you're getting your students to solve problems that you've given them to kind of practice how to do stuff, it is not effective in schema acquisition. And schema acquisition is what develops us as an expert. Now, why is that the case? Well, a major reason for the ineffectiveness of problem solving as a learning device is that cognitive processes required by the two activities overlap insufficiently. What are those two activities? Okay, so there's two activities that overlap. Well, on the one side, you've got schema acquisition, right? What you're trying to do over here is, there we go. Sorry, my spelling's terrible. There's a C there. Schema acquisition on the one side, and on the other side, you've got problem solving. Now, a major assumption seems to be with a lot of teachers that if you do problem solving, you're actually improving schema acquisition, right? So problem solving leads to schema acquisition. And what Sweller is saying is, these two activities overlap insufficiently. If you're working on problem solving, you are not developing schema acquisition. Now that's huge, hey? That's a really important thing to understand. And what he's going to do is he's going to say that in order to understand this, let's take a look at a computational model and let's take a look at some experimental evidence to provide support for the contention. Okay, so let's go to the paper itself. Now, it's a long paper and it's got quite a lot of trig and a lot of maths in it. So I'm not going to go through the actual examples, but just try and get to some diagrams which really catch what's going on. So let me just reduce the size and let's go to the computational model that he's working with. And what he's trying to do is he's trying to show the complexity in this model of what happens when you have a normal means end problem. In other words, when you give your student a problem to solve and you give them some of the stuff that they've got to use to solve it, and they know they've got to solve that specific problem. So now what happens in that situation? Now I'm just going to keep it I'm going to do it in gray so we can kind of track it. So you start, and what happens is you've got a problem statement and you've got some equations in working memory. So in other words, the student does know some stuff and does know some equations. They have some of the information that they need. And we go along and now we ask the equation with the goal as the only unknown. In other words, do we have a situation where the only thing that's unknown is the goal, is the actual attempt to solve the problem. And if that's the only thing, you've got everything that you need to solve the problem, right? You've got the equation, and the only thing you need to do is you need to use the equation to work out the goal, and the problem solved. But now the issue is that often with a problem, that's not the case. The problem is harder than that, right? So what happens is you actually don't have the goal as the only unknown. There's other things which are unknown. So there are other unknowns. Now what happens in that situation? Well, in that situation, if that's the case, you then have to add a sub-goal to working memory. Now that sub-goal you now need to try and solve before you can get to the main equation. So now when you do that, is the equation with the sub-goal the only unknown? Now if you're lucky and the sub-goal is the only thing you don't know about, and you can solve it given the current information you have, well then you can go this way, right? You can solve the equation and you can add the new known, because you've now cracked the sub-goal, you've added it as a known, and then you can use that to get the answer to the equation and the problem solved. But often what can happen is the equation with the sub-goal as the only unknown, you don't know what that friggin' sub-goal is. So what happens is you then have a situation where you've got to go back, and now you can see what's happening. Your working memory is getting overloaded by trying to continuously work out what the possible answer to your question is, and you're going back and you're going forward. And that's going to put a strain on your working memory. Now, what Sweller suggests is that there's a simpler way to do it. And the better way to do it, if you are working with a situation where you want to give your students problems, but you want to make sure that you're not overloading the working memory, is rather give them a space to explore where they can try and work out what different possibilities are without giving them a specific goal to aim at, a specific problem. Now, it's a very interesting way of doing it. So here you are, you start. You have the same situation where you have the problem statement and you have the equations in working memory. In other words, the kids or students have some equations and they have a problem statement. But the situation is that the problem statement is open. It hasn't got a specific goal. So what happens is the students can start to work on it. They can look at the issue and they can go, is the equation got a situation where it's with one unknown? Equation with only one unknown. Now, if it has only one unknown, no, well, you can stop the search because you know everything about it. If you're in a situation where the equation does have an unknown, well, then you solve the equation and you convert the unknown to a known. And you keep on going. What you're doing over here effectively is because you've taken away a means end situation where the student's always trying to find the end result and using all sorts of different techniques to get it, rather what you're doing is you're opening them out to explore different possibilities without having to get to the end goal. And because they're doing that, their working memory can basically focus on the task at hand without adding all the extra stuff that they need to answer a specific question. So here you can see that Sweller's recommending a situation where if you do want to have a problem-solving setup, what you try and do is you lift the load off the student by not forcing them into a situation where they have to try and answer a specific question, but rather allow them to explore it in an open way and find the answers as they go along. It's quite an interesting suggestion. Now, let's take a look at the experimental evidence. And in this experimental evidence, I'm not going to actually go through this example. I'm just going to say that it's got a situation where it's got a trig problem, which the students have to solve. And either what happens in this situation is they're allowed to just explore it in their own terms, or what happens is they're asked a specific question. Like if the goal of the problem is to find the length of CB, right? Here's the length of CB. And all they've got is they've got this information over here, right? And they've got to find it. And you know you've got to use sine and cos to try and find it. Now, if you give them a specific problem, what happens is the students then have to try use this information to try get the answer to the specific problem. That's a conventional way of doing it. An unconventional way of doing it is instead what you do is you give the student something like this, and you ask them to see if they can find any of the answers to any of this lengths or any of the angles, so they start to explore it in an open way. So that's the different ways of working it. Now, when they did those two different ways, it's very interesting what goes down here, guys. And I just want to show the research in it because it's really interesting. So on the one side, you have the conventional way of doing it. And I'm actually going to put it in red because you're going to see that we're talking about error scores, right? Now, what happens is the conventional means end way of doing it. Take a look at the errors that are happening. You'll see that the errors on the whole are a lot higher. The error rate, even in the solution, is a lot higher. And that's when they've got specific problems to solve in a way where they've got to go through specific steps to aim at an end result. Now, the students that were given a non-specific goal, in other words, just explore the problem and see if you can come to some answers as you go through, what started to happen was they made far less errors. Take a look at that. Even with the solution. Why? Because they didn't have working memory taken up by trying to find the specific answer. They were just exploring the area and doing what they could do at the time. So all their focus was on the specific issue and not trying to get to the answer. Man, oh man, that's really interesting. Okay, so now let's take a look at how he puts the conclusion, because it's really well put. He constructs it now as an argument, a key argument. So he says there's both experimental evidence, right? That's the example from the trig test, and lots of other examples which is used in the paper which you can go look at. And theoretical analysis. So we saw the theoretical analysis with those two diagrams trying to show that the one way of doing it, the flow chart, is far more complex and taxing on working memory than the other. And it suggests that conventional problem solving through means-end analysis may impose a heavy cognitive load. And I'm going to put that in red. Heavy cognitive load. Why? The mechanisms required for problem solving and schema acquisition may be substantially distinct. That's hectic. That's absolutely hectic. Problem solving and schema acquisition, and we know that schema acquisition is how you become an expert, right? They may be substantially distinct. By giving students problems to solve, you may actually be stopping them from becoming an expert. As a consequence, let's carry on reading. Let's see the argument. As a consequence, the cognitive effort required by conventional problem solving may not assist in schema acquisition. Now he's going to nail this argument. Since schema acquisition is possibly the most important component of problem-solving expertise, the development of expertise may be retarded by a heavy emphasis on problem-solving. My guys, this is like a chicken or the egg disaster over here, right? Take a look at what's going on over here. I'm going to do it in red because it's so hectic, right? You need schema acquisition to problem solve. But if you do problem solving, you're not going to develop schema acquisition. The development of expertise may be retarded by emphasis on problem solving. So trying to get your kids to do problem solving doesn't get them to problem solve. Man, oh man. And current theories and practices frequently assume problem solving is an effective means of learning. And currently, it may require modification. We're going to have to rethink how we do our teaching and learning based on this research and understand that schema acquisition is really important for problem solving, and the way that you do that is not through problem solving. Well, especially means-end problem solving, where you're trying to give them specific problems to continuously do.